Okay, so continuing on with our discussion of biostats, any questions from yesterday? I know you guys have had lots of time to process this, not like you had any other pressing things to study for in the meantime. Okay, so I'll assume you guys all got it down. So we were talking about the normal distribution, right? And we said, what is a normal distribution?
It's a bell-shaped curve.
So it looks like a bell-shaped curve, right? Absolutely. What does it kind of tell us about the sample that we're looking at? Should be randomly selected from the population that we're trying to apply it to, right? So if we're truly randomly selecting out a group of patients out of a population that we're looking at, it should be a normal distribution of the values that we're going to see there, right? You shouldn't be, accidentally selecting out patients who have, extreme values from one end or the other. And so that's the idea of by pulling randomly, everything should be reverting back to the mean of the population, okay? There are some other types of distributions we'll look at briefly. One of the first ones, which is not a word I just made up, as someone asked me, as the log-normal distribution. So essentially what this means is that for some values they can be more additive in nature, and so you get like a nice looking bell-shaped curve. But especially in biology and in certain aspects of medicine, you can have things that will kind of go up in kind of multiplicative kind of ways, right? So we'll look at a picture of what a log-normal distribution looks like, but it certainly doesn't look bell-shaped, right? And so at first glance, you may say, well, this is non-normal data, and that has some implications we'll talk about later, but this is actually one of those things where if you convert the scale into a logarithm, it'll actually turn into a bell-shaped curve. So here's an example. On the left side, you have a log-normal distribution, which if you were to look at that, you'd be like, well, that data looks pretty skewed. That's definitely not normal-looking data. But then if you change it over to that logarithmic scale there, you can see that it turns into a nice bell-shaped curve. Okay. So you see this, a lot in like things like tissue growth, where things can kind of grow at exponential rates. So you'll sometimes see it there. Clinically, if you're just evaluating normal medical literature, you don't see it too frequently, though. If you were to look at kind of a scatter plot, again, this line, the horizontal line there being the mean, again, it does not look very normally distributed, right? You have that one outlier that's way far out there. But if you were to convert it over, you'd see that it'd be more normal looking or more centrally distributed around that mean, right? Okay, so moving on, we're going to talk about the confidence intervals. So the first section we'll talk about here is confidence interval of a mean, and then a little bit later on today we'll talk about confidence intervals in regards to proportion. So just keep in mind there's a little bit of difference, and then we're going to be talking about these as we move forward. So when I say CI, that's just a way to abbreviate the confidence interval. What does a confidence interval mean to you guys? Anyone know what it means?
Yes.
Yes? Okay, good. So it's kind of related to the p-value.
Value will fall within that range.
Close. So it's not necessarily your p-value, but what you're saying is that when you say I have a confidence interval of, say, a sample, right? So say we're going back to that blood pressure, or I'm sorry, the body temperature example we were talking about yesterday. Remember that they were, there's one subset, there was 130 patients we looked at, and then there's another subset, there was 12 patients. Remember which group had more variability in the data? Had a larger standard deviation, right? The smaller one. Why is that? Exactly, because you have a smaller sample size, so it's more easy to have outliers, right? To have more variability in the data. As you get a larger sample size and you approximate more of the actual population, you're going to get a smaller standard deviation. You're going to get much closer to that actual mean there, right? So we said there's more variability in the smaller sample size there. And basically what we say when we have a confidence interval, we're saying that for, we're so much X% confident that the true population mean lies within this range of values, okay? So it's basically, we're not saying absolutely that the population mean is this value, because we're never going to know what the true population mean is. But we can say that we're reasonably sure to a certain percentage that it falls within this range. And so what's the typical confidence interval percentage we'll look at? Yeah, 95%. So you can say I'm 95% sure that the actual population mean is going to fall within these range of values, right? Why not 99%?
It's too confident.
You're too confident. You say, nope, I can't be that confident. Because if I'm 95% sure, that means I'm wrong in how many times out of 20? 1, right? So 1 in 20 times, that's not super confident, right? That sounds like you still have a pretty good margin for error. But that's kind of what is kind of arbitrarily picked out. That's kind of what the standard is. So very frequently you'll see 95% confidence intervals being expressed. So in this case, when you're looking at the body temperature examples, in the group that had an N of 130, we said that the 95% confidence interval for the mean ranges anywhere from between 36.75 up to 36.89. Okay, compare that to the group that had a subset of 12 patients. What do you notice about that confidence interval?
It's wider.
It's wider. Why is that?
Fewer specimens.
So there's fewer specimens, there's more variability in the data, and so that means in order to be the same, to have the same amount of confidence, we have to kind of widen our ranges a little bit, right? We can't say that, okay, well, with the larger population, I can say that I'm really, really sure, 95% sure that the range is going to be within this, the actual mean of the population will be in this range, but as you get smaller population size or smaller sample sizes, you're going to see that confidence interval start to widen out, right? In order to maintain that same 95% confidence interval. Right, so we'll look at other things that are going to affect the confidence interval and the width of it, but sample size is going to be one of the big things. So the more your samples, or the larger your sample size is, the smaller you can get your confidence interval. And we'll look at why that is when we look at some of the calculations of that in a moment. So in this case, because we're calculating the mean of a sample, there's no real uncertainty about that mean, right? Because we calculated it ourselves, we know exactly what it is. But unfortunately, we're never going to know that sample mean, or the entire population mean, because you can't really sample every single person out there. So again, that's why we use the confidence interval. It lets us know that we are not 100% sure that the population mean is going to be this value, but we can give you a range of values that we're pretty sure it falls somewhere in between, right? And so usually that's going to be good enough for most cases. So the kind of the 4 main components that your confidence interval is going to be determined by is one going to be the sample mean, right? So we know that our confidence interval is always going to center around the sample mean. So sample mean should be right in the middle there. And again, because this is based on the sample that we have and the data that we have, this is going to be the best estimate of the population mean, right? Again, confidence intervals are always going to be centered around that mean. Next, you're going to be looking at the standard deviation, what does standard deviation mean? Yeah, basically, deviation of the data from that mean, right? Because remember how we calculated that. We're basically taking the differences in each of the values from the mean. We would add those all together, divided by the number of values that we had, and then got the whole square root. So basically, if you have more values that are farther away from the mean, that's going to increase your standard deviation, meaning you have more variability and more values that are farther away from that mean. So anyway, so your standard deviation. So again, if the data is very widely scattered, you're going to have a large standard deviation, which means you're probably going to have that your sample that you're pulling from is probably going to be a little bit farther away from the actual population mean that you're interested in. If the data is really tight and your really consistent values are coming up, that means you're probably a little bit closer to the actual population mean, which means that you generally will have kind of a smaller confidence interval there. So the scatter of the data, the variability of the data is going to increase the confidence intervals you're going to pull there. So the more tightly scattered it, or the more tightly compacted it is, the smaller confidence intervals will be. So just keep that in mind, that the width of the confidence interval is proportional to the sample standard deviation. So bigger standard deviation, bigger confidence intervals, or the wider they're going to be. We talked about sample size a little bit already, so the larger the sample size, the more closely we're approximating the population, the closer we're going to be to the actual population mean. And so here, we're going to see that the confidence interval is inversely proportional to the square root of the sample size. And a lot of that goes back to when we were talking about how we calculated this standard error of the mean. But just know that, and we'll show you a graph of that in just a little bit to show you how that kind of looks. But by increasing sample size, confidence interval width is going to go down as well. And then looking at the actual degree of confidence. So is it easier, or I guess, as you increase the amount of confidence you have, what does that do to your confidence interval width? So if I go from 95% sure to 99% sure, what is that going to do? Yeah, it should widen out, right? Because I have to be safer, right? I have to increase those values in order to make sure that I can be 99% sure it's going to fall somewhere within there, right? So if I were to go, say, 75% confidence interval, what should that do to my confidence interval width? Should shrink it, right? And so we'll look at some values there that will kind of dictate how we're looking at that, but usually 95% confidence intervals are going to be the standard that we're going to be looking at. So when you're evaluating a confidence interval that might be reported in the medical literature, it's important to remember some assumptions. So one of the assumptions you have to make is going to be that the sample you're looking at has been randomly selected, or is at least representative of your population that you're interested in, right? So that a lot of times that's going to be talked about in the methods of the paper, where they'll say, these were our inclusion criteria. Here are the people that we excluded, and you'll get an idea for whether or not that the patients they're looking at are kind of representative of the population that you're interested in. So, but the assumption is it's going to be a random sampling, or at least representative of that. And then you'll find oftentimes that may not necessarily be true, but as long as it's representative and it looks close enough, that generally it can give you some idea there. And then there's an idea of a convenient sample versus a random sample. And what does a convenient sample mean, you think?
The easiest to get.
Right. So what would be?
College students for psych research.
They're perfect. Yeah. So college students for psych research. I mean, that's really easy because they're if you especially you're going to give them a sandwich or a couple bucks or something, they're more likely to respond to that versus having an actual true random sampling of people, right? So keep that in mind. That keep in mind what the actual participants were in the study, because that might be skewing some of your data to where it may not be super representative of what you're interested in. The other thing is, another assumption is that the observation should be independent, which means that people are only counted once. And then oftentimes, especially if you're looking at things like predisposition for disease, if you're looking at risk of death, you don't want to look at siblings. And why wouldn't you want to do that? So say I was looking at neonatal mortality, why would I not want to look at twins?
There might be a predisposition.
Exactly right. So maybe they have some kind of chromosomal deletion or something like that predisposes them to mortality. So that would be one case where that would not be an independent observation, because that would be skewing your results one way versus the other. So again, as long as the papers are being explicit about that and they're saying that, hey, we excluded siblings, or this is how we controlled for that, they need to at least be explicit about it. So you should assume that they have accurate data. So again, that the actual values that you're looking at are measured correctly. So hopefully you can make that assumption. And then it's actually an event that you really care about. So make sure that, in this example, we're talking about, core body temperature, that you don't accidentally have some values that are coming in that are oral temperatures, because that's not really what we're looking at. So make sure that you're assuming that they're actually testing the thing that you really care about. And then the other thing you want to see is that the population is distributed in a normal manner or a Gaussian manner, right? So again, it should be that bell-shaped curve. It should be normally distributed data. Again, there's lots of tests for normality you can run to actually see whether or not your population was truly normal. I've failed every single one of those tests that I've ever taken. You guys are definitely spent. Anywho, but again, the assumption is that the data you're pulling from should be Gaussian in nature. Okay, if the assumptions are violated, typically what you're going to see is that the confidence interval will be too optimistic or too narrow. So frequently that means that you might end up getting kind of false positive results, or you might get results that are a little too confident, more confident than they should be. And typically the actual true confidence interval is probably wider than what was actually calculated. So just keep that in mind, that if your assumptions are being violated, that the confidence interval is tending to overestimate it and be more confident than it should be. So how do you calculate the confidence interval of a mean? Again, I'm not going to ask you to calculate this on the test, but again, it's important to know the factors that go into it and how we figure this out. So one, computers do most of the calculations. We have nice, big, robust stat programs that can do a lot of this for us. One thing to know is that the confidence interval is going to be centered around the mean. So you'll typically see that the mean will be reported within, usually in parentheses, the confidence interval, and that'll be, again, on either side of the mean. So it'll say, like in our example, it ranged from, say, 36 point something to 37 point whatever. And then what you're going to be doing is you're going to be taking your standard deviation. That's one of the main one of the main components that we're going to be looking at. So you need to take into account your standard deviation. The number of values in your sample will also be included in this. And also the degree of confidence that you desire. So knowing how confident you want to be going into the calculation, you have to know that beforehand. So one of the things we're going to look at is that you end up using this t-value to decide, this is one of the components of the calculation. You're going to multiply things out to actually get your confidence intervals. And I'll show you a table of what those look like in just a moment. But just keep in mind that as a rule of thumb, if you're dealing with really large population samples, so say hundreds of thousands of patients, this t-value is going to be very, very close to the value of 2. And so what you can normally just do is use two lengths of the standard errors of the mean in either direction. So 2 times your standard error of the mean on either side of the mean value, and that's going to be your 95% confidence interval. Okay, that way you're taking into account your standard deviation, takes into account your population, all of that. For smaller sample sizes, typically what you're going to do is that you decide how confident you want to be, so whether 90%, 95%, whatever it happens to be, and then you're going to figure out what your degrees of freedom are. And degrees of freedom is always going to be calculated by your n, which is what? Your sample size minus 1. So once you get that value, your n minus 1, that's going to give you this t-value, and you're going to multiply that by your standard error of the mean, and that'll give you your 95%, or give you your confidence interval. So if you look here, you can see how your degrees of freedom are going to change the values. So you can see that as you get larger sample sizes and you get more degrees of freedom, what happens to these values? They going up or down? Should be going down, right? So that's meaning that your confidence interval is also shrinking as well, right? Because this is all proportional. So confidence intervals get more narrow as you get a bigger sample size, because again, you're saying there's less variability. You're more likely to be getting closer to the actual population mean that you're looking at. So again, very frequently you'll see that, like in a lot of these stats programs, you'll be putting in how many degrees of freedom that you have, and you just have to know that it's n minus 1 that you're going to put into there. You can see how the values are going to change based on whether you're 80% confident versus 99% confident. And what do you notice about those numbers going that direction? They should be getting bigger as you're getting more confident, right? Because as you're getting bigger, it means that you need to widen out your confidence intervals so that you can be more safe in your guess that the actual population mean lies within those values. Okay? So increasing your sample size is going to decrease your width of your confidence interval, and also being less confident, saying, okay, I'm 80% confident the true value resides within this range, will also decrease the width there. Again, I'll show you some pictures in just a second. I'll show that. One of the ways that we can represent confidence intervals is going to be by the use of error bars. And so error bars are just a graphical representation of variability of data. They can kind of reference several things. So in some graphs, you're going to see that they may be referring to standard error of the mean. They might be referring to standard deviation. They could be referring to the confidence interval. So it's important when you're assessing these graphs, you need to figure out what exactly they're talking about, as I'll show you in just a second. So in this case, this was a study they did where they were looking at how well the neurotransmitter norepinephrine relaxed the bladder muscles in rats. Again, I didn't select the study we're going to look at, but it's kind of an interesting one, I guess. But anyway, they're looking at the response. So norepinephrine causes the bladder muscle to relax, and so they were looking at the response in different aged rats when they did this. So here you can see the percentage of relaxation that occurred on the scatter plot on the left there. You see the mean kind of demarcated by that horizontal line. So the important thing to note here is that the same mean is being represented across all these bars, but the error bars are changing, right? And it's changing in reference to what specific values you're looking at. So in the first one, you see the mean with the standard deviation being referenced there, right? So the mean value is being that horizontal at the top of that box, and then you have the bars kind of going to either side of the standard deviation. Okay. Notice everything is being centered around the mean. Okay. The next one is the mean with the standard error of the mean. You notice that the standard error of the mean is smaller than the standard deviation. Again, that's always going to be the case, right? Because standard error of the mean, what did that value refer to? So standard error of the mean is going to be that value that tells you how closely your actual mean from your sample approximates the actual population mean. So the bigger sample size, the smaller your standard error of the mean gets. It just tells you how confident you are that how close your sample mean is to the population mean. So again, that's always going to be smaller than your standard deviation. Next one you're going to see is going to be the 95% confidence interval. Notice that it's about 2 times the size of that standard error of the mean, which is again for your large sample sizes, that makes sense. And then you also have the range. What's the range? Yeah, highest value and lowest value, perfect. And then your interquartile ranges. And what are those typically demarcating?
25 and 75.
Yeah, 25th and 75th percentile, right? So, and there you notice is the median, right? So median and interquartile ranges should be used together more frequently. You don't really use interquartile ranges with means, right? Because they're looking at different things. Because what's the 50th percentile? Should be the median, right? Not the mean, should be the median. Okay. Again, just a couple other ways you can represent this data. So this is all looking at the mean plus the confidence interval. So just different ways you can look at it that you might see out there in the literature. None of them are really better than the other. It just depends on how the researcher wants to represent their data. And again, sometimes your confidence intervals look like that, and that's usually not a good sign. They're that wide. Okay, so this kind of finishes up the second lecture section. So we'll go over a couple of questions. So we'll do a little Q&A session. Hopefully you guys will be able to ace all these, right? Definitely. Okay, so first thing we'll look at, so can the mean or the median equal 0?
Yes.
Absolutely, right? So it just depends on kind of what you're looking at, what your values are. Certainly, if the values kind of add up to be 0, that's possible. It can be negative. It just depends on what you're looking at. So I kind of gave away that yes, it can be negative as well. Which is larger, the mean or the median?
Depends on the data set.
Depends on the data set, right? Sometimes the median might be skewed one way or the other. Sometimes it should be the exact same as the mean. So it's going to depend on your data set. Are mean and average synonyms?
Yes.
Yes, absolutely. What are the units, or what units are the mean and median expressed in?
Same as whatever you're measuring.
Yeah, whatever your mean is, right? Because you don't really lose. None of the units actually cancel out on that one. So if you're looking at blood pressure, your mean is 120 millimeters of mercury. Your standard deviation would also be in millimeters of mercury. Okay. Can the mean and median be computed when your n is 1? Not really for 1 because you don't really have any values to average together. But 2 certainly you could do that, right? And again, if you were to only have 2 values, what would your median be?
The average of the two.
Yeah, just the average between the two. So that's what you would do if you had like an even number of observations, and you're trying to figure out what the 50th percentile is. You just would take the average of those 2 middle values. Can the mean and median be calculated when some values are negative? Yep, absolutely. Yeah, because just like we said, means and medians can be negative or 0, so absolutely. And is the 50th percentile the same as the median?
Yeah.
Yep, I already said that. Perfect. Okay. Then the answers are on here on the next slides if you guys ever forget or don't want to go back and watch the video. Okay. Can the standard deviation ever equal 0?
Not unless all of your data points are the same.
Exactly. So all the data points would have to be exact same, showing that you have 0 variability from the mean. And so it's very rare that would happen, but yes, it's possible. Could it be negative?
No.
Not really, no, because again, you're only looking at the differences between your values and the means, and basically it's impossible for it to be negative in that situation. What units is the standard deviation expressed in?
We don't have units, right? But just for the standard deviation.
No, it's the same as the.
Yeah, it should be the same. Yeah, it should be the same as. Again, we'll look at like standard errors in the mean, where the actual will end up canceling out, but with standard deviation, you still have it. Can standard deviation be computed when n is 1?
No.
No.
Yeah, no. Could it be done with 2?
Yes.
Yep, because then now you have variability amongst the data, so again, you need that there. Is the standard deviation the same as the standard error of the mean?
No.
No, right? Because standard deviation is looking at the variability in the data around the mean value you have in the sample. Standard error of the mean is more looking at how close your mean is to the actual population mean, right? And again, it's all really a factor of sample size. And so the bigger sample size, the smaller the standard error of the mean is, that ranges. So the closer you know that your actual your sample mean is going to be to the population mean. Good. Is the Gaussian distribution the same as a normal distribution? Yep, they're the same thing. So again, we'll use those words interchangeably. Are all bell-shaped distributions Gaussian? So all Gaussian distributions will be bell-shaped, but not all bell-shaped curves are going to be Gaussian, right? There are circumstances where the data could be skewed in such a way that even though it looks bell-shaped, it wouldn't necessarily be considered to be normal data. So just keep that in mind. And then will numerous sources of scatter always create a Gaussian distribution? Not necessarily, because again, depending on if things were not randomly selected, if you're skewing your data one way or the other due to some degree of bias, whether it be intentional or otherwise, not necessarily would it be Gaussian. But if it is a truly randomly sampled, a random sampling of a population, it should be Gaussian in most cases.
Would the log normal be considered Gaussian? No.
I guess log Gaussian, if you want to say that, just like, a normal distribution then that log normal distribution. So again, it becomes a normal distribution only because you have to look at it at that logarithmic scale to make it look right. Okay. All right, are values of log normal distribution always positive? You actually need to be, because you're working with exponentials and logs, so again, those would always end up being positive. Why do we look at 95% confidence?
Because that's good enough.
It's good, I know it's arbitrary. They just picked 95% confidence and they just went with it. Very frequently, you'll see, a lot of p-values are going to be expressed in things less than 5%. But the standard is going to be 95% confidence intervals you're going to be looking at around means. Does confidence interval of a mean quantify the variability? Not really, because really when you're considering variability, to quantify the variability, you're looking at the standard deviation, right? Because you want to look at how much of the values you have in your sample are kind of deviating around your sample mean. The confidence interval is basically what you're saying is that you're so confident that the mean of the population is this percentage within this range of values. So it's 95% confident that the population mean falls in with this category. So it's not really saying variability, it's just saying how likely it is that your values are going to be matching up with that population mean. Okay. Is the 95% confidence interval of a mean always symmetrical around the mean? Should be, right? Unless it were some reason you couldn't go to a negative number, it were to bump up against 0. We'll see that a little bit when we talk about proportions, but generally, it's going to be centered around the mean. Is a 99% confidence interval wider or more narrow than a 90% confidence interval? Should be wider, right? Because you need to make your guess larger in order to make sure that you can be confident it's going to fall within those values. What does standard deviation quantify? Variability in the data around your sample mean. And then I kind of already talked about what these quantify, but the standard error of the mean is going to quantify what?
Sample versus population mean.
Yeah, how close your sample mean is to the actual population mean. Okay. Are the standard deviation and standard error of the mean expressed in the same units? That one, I'm pretty sure no. Actually, no, I'm sorry. The standard error of the mean is going to still have the same units as the data, so just keep that in mind that haven't canceled each other out at that point as far as the units go. So we said which is smaller, the standard deviation or the standard error of the mean? Should always be smaller, but why should it always be smaller? Because that one's actually taking into account the population size of your sample. So basically, when you're doing a standard error of the mean, you're dividing that your standard deviation by the square root of your n. So the bigger your n gets, the larger your denominator is going to get, which means your value is going to go down, right? So that's why that's always going to be smaller. And then if you increase sample size, is the standard deviation expected to get larger or smaller or stay about the same? We expect it to. Should get smaller, right? Because as you get closer to that population size, things start to cancel out as things start to regress back to the population mean. So that's why your variability gets smaller. So as a larger population sample size gets bigger, your standard deviation should go down. Okay. So then if you increase sample size, SEM is expected to get larger, smaller, about the same. Should end up getting smaller, right? Because again, as that denominator starts to grow, it's going to drive your SEM down, so it should get smaller. So if we're looking at graphs that are showing error bars extended in one standard error of the mean each direction, what does that tell you? In your own words. So again, it's kind of referencing back how sure you are that the sample mean is going to be representing that population mean. So again, as your sample size gets bigger and those standard error of the mean bars start to get shrunken, you can be more confident that value is going to be the same as the population mean. And then why are SEM error bars used so often? Again, typically they're smaller than the standard deviation, so it's just kind of a more compact way. It shows how precisely you know the mean of the sample versus the population. Okay, so any questions on that section? All right, so I'm going to move on to the next PowerPoint. So you guys want to switch over there, we will continue on. Okay, so the next thing we'll talk about, we're going to be looking at more confidence intervals, but now we're going to be talking about confidence intervals looking at proportions or looking at ratios. So one here, we're going to define and apply the confidence interval proportions. Also looking at survival data. So this is going to be a little bit of a more morbid discussion than it already was. And then look at the confidence interval of counted data. So we're talking about things like Poisson distributions and whatnot. So again, just in case you're ever curious. Got one chuckle, that's good. Okay, so moving on, next we have our confidence intervals of proportions. Okay, so again, when we're using our confidence intervals, it's helping us to generalize the data that we have about a sample and how we can apply it back to our population. So it allows us to make general conclusions about the population we have here. So we're going to examine confidence intervals with the results that have two possible outcomes. So there's going to be kind of more of these dichotomous examples here. And so like the example we'll look at is going to be mortality. So we're going to look at rates or ratios of mortality in certain patient populations and how that's going to be expressed with confidence intervals. Now before we saw that it was relatively easy to figure out the confidence interval when you're just looking at a mean because you just need to know your standard deviation, your sample size and all of that. This gets a little bit more complicated. So frequently, again, it's done by computers most frequently. There's lots of different methods for doing this, but just when I pop up the confidence intervals here, just know that it's using a lot of the same factors, but I'm not going to go into the details on how specifically we're going to be calculating them. So again, you're going to see confidence intervals being expressed in lots of papers you go out there and see. We'll actually look at an example towards the end of this and kind of explore those in more detail. Typically, you're going to see that they really provide more information than just the raw p-value and saying whether or not a result is kind of positive or negative. Because looking at a confidence interval, I can kind of get an idea of just how wide the spread the confidence interval is. It gives me a better idea of potentially how clinically significant that result is going to be. And very frequently, you don't even need to look at a p-value. You can just look at the confidence interval and know whether something is significant or not. We'll talk about ways you can identify that a little bit later on. And again, when we're doing these, we're frequently saying things like, we're 99% confident that the true value of the parameter, when we're expressing it back towards the population, is in our confidence interval or within these range of values. Again, sometimes you'll see 99% confident, most frequently 95% confidence intervals are going to be used. So again, the width of these confidence intervals when we're looking at proportions is going to be a function of the sample size. So the larger the sample size, the more narrow our confidence intervals can be because we're getting more certain about that. The size of the standard deviation, so the larger the deviation, the more variability there was in the data, thus the bigger the confidence interval. And then also the degree of confidence you want. So the more confident you want to be, the larger your confidence intervals are going to have to be in order to contain the true value. Okay, so moving forward. So the first one we're going to look at is going to be survival rates of premature babies. So this is an example of a study that was done back in 1993. And so basically it was a retrospective study, which what does retrospective study mean?
They're looking at the data. They're not measuring anything new.
Exactly, yeah. So they're starting their study at this time point. They're looking at data that happened in the past, right? They're not doing anything prospectively. So again, this is a retrospective study they were doing. They were looking at babies that were born between 22 weeks and 25 weeks at this particular hospital, Johns Hopkins, during a 3-year period, right? So looking 3 years back in the past at the mortality here. And so what they found was when they looked at the mortality rates of the 29 infants who were born at 22 weeks, which again is pretty premature, none survived to 6 months, okay? And then looking at the ones that were born at 25 weeks, which is still pretty early, out of the 39 there, 31 survived to at least 6 months, right? So then now we can look at this and see what the actual confidence intervals are going to be when saying this. Because you don't want to say to a mother, if a baby's born at 22 weeks, like, oh, there's 0% chance he's going to make it to 6 months, right? That's not really what the data is saying here. By using the confidence intervals, we can look at the data and say a little bit more assuredly, like, okay, he's probably going to go somewhere between these ranges here. So typically, confidence intervals should be calculated, and especially when you're trying to generalize this out to a larger population. especially if you want to make any kind of inferences about the data to try to say, yes, your baby is this percentage likely to survive to 6 months or whatever happens to be. So in this case, if you were looking at the confidence interval for these two proportions, if you look at the first one, the kids were born at 22 weeks, what do you think the confidence interval would be? I think 0, I think more than that. Because if you're looking like at an average, the average would be 0, right? But fortunately, when you're using proportions, it's a little bit more complicated than that. And so the confidence interval will actually end up extending out from that 0. So we'll see that in a second. And then the 25-week babies, looking at that proportion, 79.5% survive there. Where do you think the confidence interval is going to be? Should it be completely above that 79.5%? Should it be around that number, below it? Should be around that number, right? Because your confidence intervals are always going to be kind of centered around those values there. So when you actually did the calculations and you're looking at the mortality rates, you saw a confidence interval between 0 to 11.9%. Because right in this case, you couldn't really get less than a 0 because you're looking at these proportions, right? You couldn't have like a negative. I don't know what that would be for mortality, but in this case, being 0 to 11.9%. So basically, what you're saying is that for a baby born at 22 weeks. If you were to generalize that back out to all babies that were born at 22 weeks, you'd say that you're 95% sure that their survival rate to 6 months is anywhere between 0 to 11.9%. Okay? If you're looking at the ones that are born at 25 weeks, they end up getting confidence interval anywhere between 64 to 91%. And so you would say that you're 95% confident that the baby born at 25 weeks should survive anywhere between or have a survival rate of between 64 and 91% chance, right? So how could I have made that number smaller? How could I have narrowed that range down? Yeah, so maybe if I looked at, say, 100 babies that were born in 25 weeks, maybe that confidence interval would narrow down, right? Because then I'm more closely approximating the actual population. What are some other things I could do? Or that could have affected it?
You could decrease your confidence interval percentage.
Yeah, so say I wanted to only be 80% confident, then that number would also shrink as well, right? So, but then you're not near as confident in saying that this is, the true value is going to fall within this. Because keep in mind, even though you're saying you're 95% confident, 1 in 20 times you're going to be wrong, right? So just keep that in mind. The other thing would be is if your data was less scattered. So if you just happen to have data that was a little bit kind of closer grouped together as far as survival goes, you would also see that shrink as well. So just keep those different components in mind and how that has an effect on your confidence intervals. Another good example of using confidence intervals around proportions would be like polling voters. Again, this is a very topical type of thing here. So again, if you were to randomly poll 100 selected voters before the election and say 33 of them said they were going to vote for your candidate, you don't want to just say, well, I'm assuming my candidate's going to get 33% of the vote, because really you can't say 100% that those people are going to be representative of the whole population. So you can come up with a confidence interval to say that at least I'm 95% sure that this range of people should be voting for my candidate. So other things you have to consider, though, when we look at the assumptions and whether or not those are being violated, in this case, is your sample really representative of the population of voters? Okay, so if I go to Texas, that's going to be a different vote than if I go to New York versus if I go to California. So it may not be representative, right? Unless I did, some kind of nationwide study. The other thing would be, if you had sampling errors. So say, people were to you have issues with husband and wives that may be voting the same, or if you have non-independent samples, things like that can also be changing your values over time. So again, the best you can do is just calculate the range of values that bracket to the true population proportion. So in this case, if we said, okay, we think this is generalizable to the population, we'd say 33 out of 100, and you would have a range anywhere between 24% to 42%. Which just means you can be 95% confident that anywhere between 24% of voters to 42% of voters should vote for my candidate. Okay. Again, that's all following that those same people are going to be voting the same way, say, whenever the election actually comes around. So again, the assumptions, it should be a random or at least representative sample. So all these stats, all the tests that we're doing are going under the assumption these are randomly selected patients or randomly selected samples that we're using here. And so you can see that there's easy ways to violate that, as we kind of mentioned a little bit in the polling example. But imagine if you had babies that were selected out to be somewhat sicker for some odd reason. So if you imagine, a good example of this would be something like looking at like APH versus looking at Nemours. And so APH, what type of, you're having both deliveries and you're also having, the NICU there, right? So you're kind of getting a random sampling of patients kind of showing up in the NICU versus if you're at Nemours, we don't actually deliver any of the babies there. So if you had to guess, are we having more healthy or more sick babies getting transferred to us? You probably get the sicker ones that are being born at outside hospitals that don't have, a proper NICU. They're getting transferred over to us. So if you imagine, if you're looking at our sampling, you might be selecting out for more sick children at Nemours from that standpoint than you would be if you were to say somewhere like at APH. So just to give you an idea, you have to kind of look at things like that. That actually becomes really important when you're looking at like mortality rates, because obviously somewhere like Nemours might have a little bit higher mortality rates because we're getting the sicker kids versus having a random smattering of both healthy and sick. So just things to think about with that. And then in the voter example, this is actually a good example of these polls kind of going astray. When they in 1936 there was Roosevelt versus Landon, and I guess a magazine was doing a very large poll to see who would win the presidential election. And they did something like 2.5 million voters that they had polled, and basically they were using phone books. They're using like auto vehicle registrations. And so back in 1936, how likely were you to have a phone?
If you were rich.
Yeah, if you're like rich, right? Or how you're likely to have a car if you're. So they're really looking at more kind of upper middle class people that were voting, and not necessarily some of the poorer sector. So of course, when they actually did the true election, Roosevelt ended up winning, even though Landon was the one that was kind of coming out ahead. So just keep in mind that if you have bad sampling methods, you're going to come up with the skew results. Again, looking at independent observations, that should also be in your assumption there. So if you had, say twin that ended up in the NICU that were both born at 22 weeks, obviously, they can maybe have some influence on one another that may affect your results. So really the results should be independent from one another. Again, if you were doing polls and you were asking some, kind of leading questions, like is it, if you were a monster, would you vote for this candidate? And, you can make up some really bad questions to kind of skew the results your way. So, the types of questions you're asking can really affect your results as well. You should assume that you have actual accurate data. In the infant example, it's pretty clear cut whether birth or dead or alive or dead. But in the voter example, if you had someone who was recording opinions incorrectly, like I said, if there were leading people to answer one way or the other, that could definitely skew your results there. Okay, so again, what does a 95% confidence interval really mean? It just means that the true population value is going to lie within, we're 95% sure it's going to lie within this range of values or not. So keep that in mind that we said, even if you did this several times over, 1 in 20 times, you could be incorrect, right? So a good example of this is this slide here where you can see that they did basically the same test 20 times in a row using the same mean, but looking at the actual true population mean being denoted by that horizontal line there, you can see that again 1 in 20 are going to fall outside of that, and that's just due to random chance, right? Because we can only be 95% confident that our value, the true value, is going to lie within that. Does that make sense? Okay. Okay, so next thing to look at is whether or not you're actually going to be quantifying the event that you actually care about when you're doing these results. So again, in the infant example, we're looking, definitely at the thing that we're looking at. If you're looking at mortality, like you're looking at whether or not the patients, lived or died. If you're looking at things like polls, or looking at survey results, time can be an important factor there. So if I were to poll people 6 months ago who they're going to vote for versus who they're going to vote for today, things could have changed quite dramatically from then. So again, extrapolating that data can be difficult, especially if people say one thing and then decide to vote a different way when they're actually in the poll there. A good example of this, another election was Dewey versus Truman, where they actually were doing polling that started back in September, and the newspaper actually published out and said that, hey, basically, Dewey defeats Truman, and that ended up totally being false. Totally ended up being the opposite. So just keep in mind that, make sure that the events you're looking at are going to actually be accurate to what you're looking for. Okay. When we say confidence limits, that's just basically talking about the range of the confidence interval. So, basically the high and the low values of that. So if you ever hear that, that's what that's referring to. And again, this is all just going to be an estimate. So we're just estimating that, we can say that 95% confidence that the true value lies within this range. But again, we can never say with 100% certainty that this is going to be true. Just another good graphical example of how your confidence intervals can change or widen and narrow based on how sure you want to be about what you're saying. So again, more narrow confidence intervals come about when you're trying to be less sure about something. So if I say 80% sure, we can have relatively narrow ones, but I'm just less confident that the actual value is going to fall within that range. And this is another thing we mentioned, that as you, because this is a factor of the square root of the n, or your sample size, as you start to increase your sample size, you're going to see the confidence interval also start to drop. Okay, so larger sample size, smaller confidence interval. Here's an example, because you can use proportions. We kind of mentioned this back in the infant example, but because proportions can go down to 0, you can sometimes have lopsided confidence intervals. So this is one of those examples of that. So just keep that in mind. If it looks odd and it's not completely symmetrical around the mean, that's not an error. Sometimes it just makes sense for the type of data you're looking at. Okay, let's go ahead and take a break now. We'll come back in 10 minutes and continue on with survival data. Okay, so I'm repeating this slide real quick. I just wanted to reiterate a point just to make sure I'm kind of driving it home. So when we're talking about 95% confidence intervals, say for instance we're looking at the 25-week gestational age babies that were born. Essentially what we're saying when we generate that confidence interval is we're saying that we're 95% sure that the actual survival rate for someone, child born at 25 weeks is somewhere between 64 and 91%. Okay, so if you were to generalize this out to the actual full population of babies that were born at 25 weeks, you would say that, okay, they either have somewhere between a 64% chance of survival at 6 months, or they have a 91% survival at 6 months, okay? So again, if we looked at a larger sample size of those babies, we may be able to narrow that down to say, well, maybe it's more like 68 to 84, whatever it happens to be. So just keep that in mind, that this is just our 95% estimate. This is how sure we are that the actual value will reside somewhere between those values. Okay? I think you got it. Okay, so moving on, we're going to look at survival data. So again, this is going to be useful for, you can apply this not only to survival data, but also things that really can only happen once. So, for instance, being born kind of only happens once. Getting a disease that can only really happen once, so say like HIV contraction or something like that, like you can't get rid of it and then you have it again, but most oftentimes you're going to see this data being kind of referred to in terms of survival data or death, because again, that's pretty dichotomous variable there. You're either alive or you're not. So when we're looking at survival curves, basically what we're going to be saying is that we're plotting the time to any well-defined endpoint or event. So again, whatever the event happens to be that we're looking at. It has to be a one-time event that does not reoccur. So again, death is the most common one. And then you have to know the survival time for each subject, or when the data was censored. We'll talk about censoring data in just a little bit. But essentially, you have to know the exact time of when that event occurred, because you can use this data to not only look at a sample of a population, but you can also do comparisons of survival between different, say, treatment groups or whatever it happens to be. And so having that data be exact and knowing when that event occurred is critical for that. So when I say censor survival data, does anyone have an idea what that might mean? Like they said a bad word and I had to censor them. So this is going to be more for patients who have fallen out of the study for one reason or another, and you're going to exclude that data from the analysis. Okay. So oftentimes you may have patients that are lost to follow-up. Say, for instance, you said in your study, in your methods, that you were going to rule out patients who were, died of a different cause than what I was looking at. So if I was looking at cancer deaths and I had a patient die of a car wreck, is that necessarily related to one another? Maybe not. So maybe that's something I say in the beginning of my study, that, hey, we're going to exclude, we're going to censor those patients that die from a non-related cause. Very frequently, though, because you want to make sure that you're as inclusive as possible and make sure that there's no bias in your data, typically you want to include as many of those patients as you can, but in some cases you still are going to end up censoring them. And it's important to make sure that the article writers are being explicit about why patients were censored for one reason or another. So again, whether it be that they moved, they're lost to follow-up, or potentially if they had survival time that lasted past the end of the study period. Because typically you're going to see these studies being done over the course of several years in order to get enough data to say kind of what kind of mortality you're going to be looking at. So again, censored observations in general should not be removed from the analysis. Like that way you can still account for them, you can still include them in your analyses to make sure you don't have any unnecessary bias in your data. And again, you need to know how long the patient's been alive for, especially in regards to the protocol of the study. All of that needs to be kind of decided prior to actually beginning the study, so that way you don't go and try to change things later on, because that can induce bias. Any information that happens after the end of the study period should not be included. So if a patient survives for that long period of time and then they end up dying, after the study period ends, you don't want to include that data, because again, that's not really what you were looking at. So, for instance, here we have a set of data for patients who were involved in a survival analysis. And so, if you had to imagine which ones would be considered censored data, or which one would be censored patients? So the one that moved and is no longer on protocol, yeah, that would be a good one. But who else? Yeah, the last one died in a car crash, so maybe you might censor that one because it might not be related to what you're looking at. And then
The fourth one.
yeah, the study ended. Yeah, so that person was still alive at the end of it. So that could be a potential person you may decide to censor. Very frequently, though, you would still include those patients into your analysis. So again, looking at the data, there were 7 patients in the study. 3 of them ended up being censored. Just saying kind of what the different reasons were. When you're looking at patients who died from an unrelated cause, typically you just use the time period that they died at as kind of their final endpoint for that. And again, and when I say intention to treat, what do you think that means? So intention to treat is a term where even if the patient was, say, randomized to one group or another, or I was including them in the study, and say they were to fall out of the study, they were lost to follow-up, or say they ended up dying from a different cause, you still include them in that analysis. So when I say intention to treat, that just means you're still going to include those patients in your analysis, even though they didn't really follow the letter of the protocol that you had set up for them. So you include to your last known survival point. So say, for instance, you're trying to compare mortality in 2 different cancer treatment regimens, right? You're trying to show that one was caused lower mortality than the other. You would basically use the last time point that you knew that patient was still alive and just carry that out. Like they were alive for that period of time and then they just never died that you know of, right? Or if a patient died from a different cause, like in the car wreck case, you would still include that in your analysis of the patient who died at that point. So even though it may not be related to the treatment, whatever it happens to be, you still would include that data. Yeah, so a lot of times you do that because otherwise if you start excluding patients kind of willy-nilly, then some people can come back and say, well, these are biased results, you didn't include these patients. So very frequently you'll see them either being included, or if they are excluded and being censored, the researchers are generally going to be pretty explicit about why that was occurring, what the specific reasons was. Okay, so again, you would look at the data, you would look at the start period from when they entered the study to the end of their study period, and basically they would just have a code assigned to them. So 1 being for when they died, and 0 if they were still alive at the end of it. Or in here, in these cases, these patients were 0s, so they were being censored out from that data. So there's kind of 2 methods for creating a survival table. We're going to mainly talk about the Kaplan-Meier method, but the other kind you can do is this actuarial method, where essentially you would have patients, you'd have a standard kind of time frame on your x-axis, and as patients entered different points in the study, you would just include them in that analysis at that point. So patients who entered later would kind of be farther along on the x-axis than patients who entered earlier in the study. Very frequently what we do with Kaplan-Meier curves is that we're going to use all patients, whatever their start date was, as time point 0. So that way you can say that at the beginning of all the study patients period, you had 100% survival, and then as time went on from there, you have deaths that can occur. So it's easier to make comparisons between different groups, and it kind of puts all patients on the same playing field, so to speak. And I'll show you what some of those look like in just a second. Again, this is very frequently these curves are done by computer, not done by hand. And essentially what you're just doing is at the beginning of each day, you calculate how many patients are alive divided by the total number of patients. You take the number alive at the end of the day divided by the total number alive at the beginning of the day. And you see how this curves have kind of a stepwise approach to them as patients start to die off throughout the period. So again, if you were to look at the study data we were looking at previously with those 7 patients, again, in this case, you're going to include all of the censored patients. You would look to see the survival rate as time goes on. You see the percentage is going to be dropping, and so you can kind of see how that stepwise approach kind of gets introduced into the graph, so we'll see in a minute. So there's a couple of different ways that you can show this data. Very frequently, I'll probably see it as the lower right graph. This is how you'll see it reported in the medical literature. What do you think the ranges are in that shaded area in the bottom left graph are? Yeah, it's your confidence interval. So it's basically your 95% confidence interval for the survival rates at various time points going on. So you can say, for patients who have whatever your outcome that you're looking at, at 4 years, the survival rate was such and such percentage, and the 95% confidence interval was somewhere between, some lower bound and some upper bound. So that's basically displaying there in that shaded area. But again, very frequently, the bottom right one's the one you'll see in the medical literature, that kind of stepwise approach as the survival goes down. And then you can see as well, like on those points where either, like on the bottom right, the censored patients get demarcated by a little dot, or they could be little tick marks like you would see in the one on the bottom left. So just different ways that represent the same data. So very frequently you will see people talk about the median survival time. It's a little bit easier to talk about the median survival time than the average or mean survival time. We'll talk about what that is in a second. But basically it's going to be the point where 50% of your patients were alive and 50% were dead. Okay, that's going to be your 50th percentile. That's your median survival time. And again, this is easier to calculate than the mean survival time, because that would mean that all of your patients passed away. And very frequently in a lot of studies, you're going to see that you'll have some degree of survivability at the end of the study period. Obviously, if you did it out for a long enough period of time, everyone dies eventually. But it's a lot easier to do median survival for these study periods. So. And again, frequently this is also used because you can do better comparisons between, say, 2 different treatment groups, or whatever your intervention is going to be for a study. You can compare the median survival times. It's a little bit easier to do than looking at like a mean survival time. Frequently, you'll see cancer outcomes being reported as 5-year survival rates. Again, it's pretty arbitrary. I think it's kind of more of a matter of tradition at this point. But again, if you're looking at cancer studies, very frequently that's how you'll see it being reported as. Okay, so looking at assumptions, again, you want to make sure that the data you're looking at is not violating any of these assumptions, in order to make sure that you can take actual good data from, or good information from the sample that you have, and be able to generalize it back out to the population, right? So the second you start to violate these assumptions, the less generalizable the data is to the population, the less likely you can make any kind of useful inferences about that population. So again, the first one, again, you should be looking at a randomly selected sample. It should be, or at least representative of the population you're looking at. You want to also be looking at independent subjects. So again, the same thing we talked about with the infants is that, siblings may have genetic predispositions to certain things. Certain cancer patients may have, if they're related, they may have similar mutations of the cancer that may or may not respond to treatment, whatever it happens to be. So you want to make sure that the data is going to be independent there. And again, no patient can be counted twice, because again, this is always going to be, kind of a live or dead, yes or no kind of thing that you're going to be looking at when you're looking at these survival analysis. The entry criteria should really be consistent. So this is going to be more important assumptions that are more unique to the survival analysis. So again, if you're looking at, say, patients are being entered into the study once they have a diagnosis of, say, breast cancer, it's important that the rates of entry into the study don't change over time, or how you decide a patient who's going to get into the study changes over time. So imagine, if you will, that you were doing a long-term study, say over 5 years, looking at breast cancer survival rates, and you're able to enter patients in based on your typical diagnostic methods. But now all of a sudden you have a new diagnostic method that captures these patients, say, a year earlier than you would have with standard measurements. What do you think that would do to your survival? you probably increase it, right? Because you're catching patients earlier, you can start treatment earlier, chances are your survival rate should go up. So now all of a sudden that's kind of skewing your data. So you want to make sure that patients who are being included in this study are all going to be done by the same very explicit criteria. So that's where we talk about inclusion criteria and exclusion criteria. It's important that's going to be adhered to throughout the entire study period. And then you also want to be looking at the endpoint being defined consistently. Again, so do the deaths, do all deaths count? Or are you only going to look at cardiovascular related deaths? Are you going to only look at you're going to exclude or censor out say traumas or things that are unrelated? You have to make sure that you be very explicit about that as well, because otherwise there's ambiguity. There's more risk for bias entering into your results. Your starting time should also be clearly defined so that all patients are being entered in at the same time period. So it should be a very objective date. So it should either be the time of first diagnosis, first hospital admission, start of treatment, whatever it happens to be. It needs to be the same for all patients. You definitely don't want to use patient recollection to do this. Like, oh yeah, I think I was diagnosed 6 months ago. Not good enough. You need to actually have a real date in their chart to reference back to. And again, patients who die early on, before they even get treatment, should not be removed from the analysis. So again, this is that intention to treat that I mentioned, where even though they didn't get a chance to start the protocol, they should still be included, because that way you can still limit the amount of bias getting into your results. Okay. So again, we're assuming that we're not censoring unrelated data that's unrelated to the survival. It's really only valid if we are, the reasons for the censoring are being expressed. So it's important to really follow those, make sure those are being explicit there. Because again, you want to consider, if a patient dropped out, say due to drug treatment, and adverse effects were too bad, that can really be skewing your data some, right? So it's important to look at things like that. Maybe they could be having disease progression that caused them to drop out, or whatever it happens to be. That you want to include all those patients in your analysis because it could all be relevant. And then sometimes you can actually, we'll see sometimes studies will do the analysis before and after censoring to make sure that the results are similar. Otherwise, if they're wildly different, then obviously something's going on there. So sometimes you may see that being done out there in the literature. You're hoping, your assumption is that the average survival time doesn't change during the study. So these results would only really be meaningful if those survival rates are similar throughout the time period. So again, imagine if you were comparing patients who were receiving, or if you're looking at cancer survival rates, and all of a sudden there's a brand new treatment that comes out halfway through that increases your survival rate pretty significantly. That's going to skew your data pretty significantly there. So just keep that in mind, that the survival rate should be similar over time. Other things that you could look at, potentially you could look at the percentage of death being represented rather than just the actual number of patients who die over time. So sometimes you'll see this graph look a little different. Just be aware it's a different way to represent the similar data. But that's probably infrequent. You're normally going to see again, that one that I mentioned is that really stepwise looking and then kind of going down towards the right. Okay, so again, why are we reporting median survival time rather than the mean? We mentioned that the mean survival time can only really be computed if you had every single patient die at the end of the study period. But by using median survival time, it's a little bit easier to hit those numbers at that 50% mark rather than waiting until the very end. Okay. Then moving on, one of the last sections we'll talk about for this is the confidence interval of counted data. So here we're going to be talking about the Poisson distribution, and so this is going to be useful for talking about events that change over time, or things that happen at a certain rate but have some variability into it. And I'll give you some examples of this in just a moment. But by looking at the number of counts over a certain period of time or certain intervals, this will be referred to as a Poisson distribution. And from the number of events that are occurring, we can actually generate confidence intervals here as well to determine how likely it is that the results that we're getting are representing the true population mean. So a good example of this is if you were to receive mail. Say that typically on a given day you're going to receive 4 pieces of mail. And that becomes your expectation. You assume, yeah, on average I'm going to get about 4 pieces of mail a day. Certainly there's going to be a spread to that. Some days you're going to be getting a little more, sometimes a little less, sometimes you might not get any mail at all whatsoever. But given only the average rate for a certain period of observation. So again, we'll be looking at pieces of mail per day. That's how we would do our measurements there. And assuming that the process that produces the amount of mail that we're getting is random, then basically what we're going to be seeing is that we can tell from a Poisson distribution how likely it'll be that we may get 3, 5, or any number of pieces of mail in a given day. That's basically what this is going to be telling us over a certain period of time. So it's going to help us to predict the amount of degree of spread around a known average that can occur. And again, this is going to be done over repeated measurements throughout time. And then we'll see that we can actually end up getting, when you're having like small values of p for these, when you're actually getting p-values from these distributions, you can simulate a binomial distribution, which in case you'd actually have end up having 2 peaks that can occur in some of those distributions. So we'll talk a little bit about that later. So again, the Poisson distribution is going to apply when we have events of something that can be counted in whole numbers. So frequently you're going to see that we can have ways to deal with dealing with fractions of numbers, but typically we're going to be counting this with whole numbers. The occurrences have to be independent so that one occurrence doesn't diminish or increase the chance of getting another one. So again, getting one piece of mail does not necessarily mean you're going to be getting more mail in the future or less. They're going to be completely independent. And then the average frequency of occurrence for the time period is known. So you need to know what your average is when you're doing these measurements. And then it's actually possible to count how many events have occurred. You're able to get a good, accurate representation of how often the event is occurring. So again, we'll show you a figure in the next slide of a Poisson distribution. The one that we're looking at here is going to be looking at background radiation counts that occur. So again, we have say some kind of measure, some device that's measuring radiation counts that are occurring over a period of time. Basically just looking at background radiation. So you might see this in say some kind of imaging department or something. And you'll see the range will kind of go from say just a few counts to maybe a few dozen counts per minute the device will actually detect. And then by using that data, we can actually look at the distribution of the counts and actually see confidence intervals for kind of what range that you can get from that, or basically the spread. And so I'll show you that in just a second. So here would be 2 examples. So say in the first one on the left, you have the mean getting about 1.6 counts per minute versus the one over here on the right getting 7.5 counts per minute. Just notice that typically these spreads or these graphs are going to be asymmetrical. So even though you may have randomized data that's normally distributed, these will always end up being asymmetrical. And that's mainly because you have a 0 mark, right? Your basement is always going to be 0. You can't really have negative mail that you're getting unless someone's, I guess, stealing it from your mailbox. But we're not going to assume that's happening. Should have at least some kind of positive integer there. Does that make sense? Okay. Again, so it should be asymmetrical. Given, so say that we have a rate of 3, say that's our average, the range of variation is going to end with 0 on one side. So that's why it ends up making it asymmetrical. As your rate gets bigger, you will end up seeing that it will end up looking more like a normally distributed bell curve, especially as you get farther and farther away from 0. And as your counts go up, you'll end up seeing that look a little bit more like you would usually expect to see with a Gaussian distribution. So this is useful for helping us to determine, say, the uncommon events that are occurring, say, in time or in a particular space. It has a convenient property that the mean value that we have here is actually equals to its variance. So we'll see how that's important when we're looking at the confidence intervals there a little bit later. And it's also going to be useful in evaluating the clustering of rare events. So if you were suspecting that, say, you were having cancer clusters occurring around, say, a specific area where there might be some kind of exposure to a toxin or something like that, this is useful for helping to look for clusters of that by looking at changes in the distribution over time. So again, the calculations are going to be made by looking at the number of events that occur per unit of time, or a number of objects in a certain volume. So those are the main ways you're going to be seeing this being represented. And again, the assumptions for the number of events that are occurring is that basically the event is clearly defined. So that way it's very unambiguous what will count as an event, which one does not. So again, if it was like cancer clusters you're looking at, actual diagnosis of a particular type of cancer. The event should occur randomly and not be influenced by other events that are occurring there. So again, if you had different people getting diagnosed, it's not like one person was giving it to someone else who gave it to two people. So it really needs to be independent of each other. The average rate shouldn't change over time. And then each event is only counted once. So that way, basically, one event does not get counted twice and can change your rate that's occurring there. So basically, it needs to only be counted once. So the assumption on the number of objects that we're looking at, so the objects are randomly dispersed. Hopefully you're not getting any clumps. So again, it should be randomly distributed throughout that range there. Again, each object's only counted once, and there shouldn't be any ambiguity about what to count. So say, for instance, you were looking at cells under a microscope, making sure that every investigator who's looking at those cells is able to count the same number or knows what to count in order to make sure the results are consistent. Otherwise, you're going to get bias entered in, you can have some issues there. So using the Poisson distribution, we can actually compute a confidence interval. In order to do that, you need to know the actual number of events that are counted in the volume or the number of events that occurred over the time period. Again, so it's having all the values there. That the background radiation example, you have that detector looking over those periods of time and collecting that data. You can get an average rate that's occurring. And then based on that information, you end up getting a confidence interval that can be generated from that. So for instance here, you can see some of the values that you can use. Remember when we looked at the confidence intervals for looking at means, you saw a table that had the t-values that helped us to figure out what basically how wide our confidence intervals are going to be. This is a very similar table. Just know that those exist. Usually the calculators are doing that work for you, and it's going to be determined based on the number of counts that you're actually getting. So we'll talk about that in a second. So another good example of this, not necessarily medically related, but in case you guys are hungry, which is probably getting close to it, right? Yeah. So we're going to look at raisins in bagels. I don't know why you'd ever pick a raisin bagel, but just go with it. So let's say,
It's gonna take too long.
yeah. So let's just say we have a bagel that you find 10 raisins within it. You can assume that the raisins are randomly distributed. So we'll assume that every bagel that's coming out, no matter how many raisins it has, it wasn't necessarily due to clumping or anything like that. And you can assume that the average number of raisins per bagel isn't changing over time because the recipe is staying constant, right? So we're assuming there's no changes from day to day. Every bagel maker is making the bagels the same way every single day, right? In this case, because we know there can be a range of raisins that end up in the bagels, you can generate a Poisson distribution that can occur here. And so based on that, if we went back and looked at our rate, which is 10, that's kind of our average rate, you can go back and look at the confidence interval back on that table is between 4.8 to 18.4. The reason why we can use that average to generate the confidence interval without looking at things like the standard deviation is because we already said that with Poisson distributions, the average already is the variance. So by using that, you get this confidence interval, and so that you can say that with 95% confidence, any bagel that comes down the line should be having anywhere between 4.8 or I guess 5 and then 18.4 or maybe 19 raisins that will pop out, right? So that's kind of your 95% sure that the rate will be somewhere between that. So, and then similarly, if you're looking at the radioactive counts that we were looking at previously, so say you counted 120 radioactive counts in 1 minute, basically if you're assuming that they're occurring randomly and independently and the rate's not changing, again, you can still use a Poisson distribution. And so looking back at that, if you were to get that C value back from that table, that'll tell you that basically you're 95% sure that if you were to randomly sample counts during a 1 minute time period, it'll be anywhere between 99.5 to 143.5. Okay, so this is kind of giving you an idea of what kind of spread you're going to have and what kind of random values you can generate with 95% confidence. Frequently, you'll see, especially events that occur uncommonly, being expressed as person years. Has anyone heard this kind of term being used before? So it's basically being said that if you had, person year, if you had one person who lived for 1 year, that's one person year, right? I could have 10 people live for 10 years, and that would be considered, so 1 person year. You could end up kind of adding these up and kind of changing the way you look at it. So eventually you could say, if I had, say 10 people I'm trying to think of a good example of this. Basically just referring that, a certain rate per number of person years. So it could be, say 500 people over a 2-year period, or it could be 1 person over a 1,000-year period. This is the kind of rate that you'd end up getting. And so again, it can be delineated. It's just kind of an easy way to compare different rates together by looking at, without having to look at the actual number of people that you're sampling there. So for example, if we were to look at exposure to an environmental toxin that was causing death, but it was somewhat very rare. So say, for say 500 people over a 2-year period, which again would be 1,000 person years, you only had 1.6 deaths that occurred on average, right? So it's a very low occurring kind of event that's happening here. What we can do is actually figure out the 95% confidence interval, but we said we need to have a whole value here, not using decimal points. So basically what we can actually do is convert this over to, instead of 16 or 1.6 in 1,000 person years, you can just say 16 in 10,000 person years, right? Same proportion being reported there. Now at that point you can set your C value at 16, and you can find out that your range is anywhere between 9.15 to 25.98, around 26 or so. So you can say that with 95% confidence over 10,000 person years, that your range should be anywhere, the number of deaths that occur from exposure to this toxin occur anywhere between 9 to 26 times. That makes sense? And then you can then divide it out and actually get back to the same 1,000 person years that you were talking about previously, and just divide it out and say, okay, anywhere between 0.92 deaths to 2.6 deaths per 1,000 person years. So again, just another example of how you can use a Poisson distribution to give you an idea of rates that you get from a sample, and how you can apply that back to the general population. So again, all you really need to compute the confidence interval for this count is you just need the count from one sample. And it's essentially your basic calculation of the number of events or the objects that were actually observed, right? So that's why it's important that you make sure that the observations are occurring consistently, that you have a very clear definition of what the actual event is. You typically don't want to normalize to a more convenient scales, which means that you don't want to necessarily do any kind of rounding or anything, because again, that can have a big change on your values over time. But essentially, what you end up seeing here is that when you have large C values, very similar to what we saw with those T values, and you get very large, you can end up using this value of 1.96 in order to get your 95% confidence interval. Don't really focus on that point too much, to just realize that those C values are really the big thing that's needed to help generate that confidence interval. So again, we'll show you in the next slide, again, some radioactive counts that occurred. We'll look at one that occurred in 1 minute, and then we'll look at another measure that was done over the period of 10 minutes. And so looking at this, which one do you think would give you a better estimate of the actual occurrence that's happening? Yeah, so usually if you're looking at longer intervals of time, you're going to see a little bit more accurate representation of the actual average. And so counting for longer period of time gives you more counts, and so that gives you a bigger C value that you can put in, so it allows your confidence interval to kind of shrink down so you can be more confident in your actual answer. So if you look here, you can see that if you were to do counts over 1 minute, they can be pretty far spread, versus if you were to do the counts over a 10-minute period, those averages ended up coming down and regressing back to that mean. So even though the mean is very similar between the 1 minute and the 10-minute, you can see just the spread in the measurements you're getting there. So again, with the advantage of using longer time intervals, let's say we're going back to our raisins and our bagels. Let's say you were to count 7 individual bagels, and you end up finding a range there anywhere between 9, 13, 7, 12, whatever it happens to be. So in total, instead of just going off a value of the original whatever it was you found, the nine raisins, by looking at 7 raisins in 7 bagels, basically what you can do is that you have an average of 10 raisins per bagel. But the CI, or the confidence interval, should really be based off of that total count that you had there. So you're going to use that number of 70 as your C value. So by doing that, your confidence interval will range anywhere. The 95% confidence range will go anywhere between 54.5 raisins per 7 bagels up to 88.4 raisins per 7 bagels. And then you can just divide that 7 out, and then you'd have your 95 confidence interval for just 1 bagel. But by using more counts, you can see that you can get a little bit smaller confidence interval, you can be a little bit more sure about your values being representative of the true population mean. Okay, so again, it's important that we're at the end of the steps. We're going to be normalizing for time or volume only after you've kind of calculated the confidence interval, because otherwise you can get some bad rounding that can occur that can really skew your data there. So just keep that in mind when doing those counts. So this is kind of the last section I want to talk about. I want to talk about some application of confidence intervals and how it how you would see it in the medical literature and how to make some sense of it. Okay, so this is an example of a study where they were looking at ramipril, which you guys remember as what kind of drug? It says it right there. Yeah, it's an ACE inhibitor, right? So anyway, what we're going to be doing, it was tested for use in patients who had a high risk for cardiovascular events. Okay, so this is a study that was published back in the New England Journal of Medicine. You guys have heard of that one, right? Yeah, it's a big one. And so they looked at quite a big number of patients, or looking at over 9,000 patients, and they got recruited into a randomized, double-blind controlled trial. So if I say randomized, what does that mean to you guys?
Some people get the dose, some people don't.
Yeah, so they basically got randomized. Yeah, so you weren't like, okay, you're going to go, you get drug, I don't like you don't get drug. It's not like that. I'm just kidding. I like you just fine. Anywho, so that's randomized. Double blind, what does that mean?
The investigators and the patients don't.
Right, so if I had like a single blind trial, what would that mean?
Just the patient doesn't know.
Yeah, the patient doesn't know what they're getting, but in this case, the patient and the provider doesn't know what they're getting. Really, only the people who are running the study actually know. When I was working at Nemours and I was kind of filling in for the investigational drug pharmacist, like it was big deal. Like really only the pharmacist dispensing the drug knew. And again, that's going back to that study where we're doing the lumbar punctures to inject the drug for those SMA kids. It was a big deal because the parents were always trying to figure out whether or not their kid was actually getting a drug or not. They're trying to they would even say that because when we were giving out placebo, we didn't actually have to make anything in the IV room. We basically just had a vial that we handed over to the study coordinator, and so actually they wanted to make sure that when we were delivering the drug, we still wore scrubs like if we were going into the IV room, so that way we, the kind of clothes we had on. If I showed up with this, obviously I was in the IV room. That didn't confuse them and get them to think maybe they're getting drug or not. Anywho, so the blinding is really important. You don't want to ever break the blind, because otherwise you end up introducing bias into the study. And then controlled trial just means what?
Like you have a group that doesn't get the medication to compare.
Yeah, so I have a control group. So again, in this case, it was ramipril versus placebo. Neither patient nor provider knew what they were getting. Just the study group knew what patients were being assigned to. Okay, and so basically what they did, they looked at a number of cardiovascular outcomes, right? So in the first case, they were looking at cardiovascular events, including death. And so what they found is they had 651 out of that 4,600 patients have a cardiovascular event. So it's around 14%. You see how that's being denoted there. You see how they have the in parentheses the percentage mark. That's how you know what the percentages are being represented there. And then versus 826 in the next group. So what does that mean? Does that mean that ramipril decreases your incidence of cardiovascular events? So we'll look at it. So we'll see. So what they ended up doing is something called relative risk, which we'll actually look a little bit more at detail later on. But basically what it's saying is that what's the patient who received the intervention, what's their risk relative to the group that did not? Okay, and so what we saw is that the relative risk ended up being 0.78. So what do you think that means?
78%.
So they had so the people that got ramipril had 28% less cardiovascular events than the group that got placebo. Does that make sense? Because you can basically just divide that out and figure out, okay, that they had a 22% less chance for having a cardiovascular event. So then, what's that? The value in the parentheses behind that 0.78?
Range, confidence range.
Yeah, it's your 95% confidence interval. So they're saying is that if you were to extrapolate this out to the general population of these patients who are included in the study, they would say that the actual reduction in cardiovascular events was anywhere between a 30% reduction or a 14% reduction. Okay. And I'll tell you that actually is a statistically significant reduction. And one of the things you can do is by looking at relative risk, if it crosses the 1 mark, so say it were to go from say 0.7 up to 1.2, that would tell you that it's not significant. but because it's less than 1, that tells you that, yes, this is a significant result. So I don't even have to see a p-value to know that, right? But that confidence interval is just telling you what the range of results are going to be, with 95% confidence if you were to apply it to the general population. That make sense? So there's a real-world application for confidence intervals. And then looking at, how about death from non-cardiovascular causes? Do you think this would do you think Ramipril would have a big cause on death from non-cardiovascular causes? Probably not, based on what you know about the drug and the mechanism. And so that's kind of bared out in the thing here. So if you look at this, more patients in the Ramipril group had a death from a non-cardiovascular cause than the placebo group. So if you look at the actual value, 1.03, that means patients who got Ramipril actually had a 3% increase in events. Now, is this result significant? You can tell it's not, because if you look at the confidence interval, you can see that it went anywhere between, say, a 15% reduction all the way up to a 26% increase in risk. So because it's such a wide confidence interval and actually end up crossing the 1, it's non-significant. So that actually you can't take any results away from that particular aspect of it, that outcome. And then looking at death from any cause, we can see that the Ramipril group had what kind of risk reduction? About 16%, right? So 16%, and look at that confidence interval. It goes anywhere between 25% decrease to a 5% decrease. And so you know that the true patient, the true population result would be, anywhere between those values in 95% of cases. And so that would be significant because, again, it doesn't cross the 1. So it's almost there, and almost maybe a little less significance, but it ended up retaining it. And so that is a statistically significant result. So again, looking at your confidence intervals can tell you quite a bit. And obviously you can look at things that have very wide confidence intervals. So if you look at the one from the non-cardiovascular death, you notice it ranges very widely as compared to some of your other results. So especially the other two, much more narrow confidence intervals, that leads you to believe that, yes, that result is probably pretty accurate, that actually was a true reduction there. Everyone with me so far? Okay. So again, just kind of some more details, kind of exploring kind of what we already talked about here. But again, confidence intervals, you're going to see a lot of them. They're used very frequently in the medical literature. And so just keep that in mind as what their significance is going to be as we continue talking about them, especially when we're talking about comparisons of different groups, especially like different treatment groups and things like that. So I think that's it for this section. Do you guys have any questions? You guys' minds are blown. Yep. We're done with epi biostats for the week, so that's good. All right, I'll post this up and then I'll see you guys next time.